Question 6. You are supplied with 6 identical cells, each of EMF 1.5 volts and internal resistance 0.3 ohms. State the EMF and internal resistance of a battery of 3 cells connected in series. So when we're doing this like this, we should represent each one after the other if we want to draw a diagram. And if we're thinking about our standard rules, we know that resistors in series just add up, but also that cells in series add up. This is Kirchhoff's second law applied. The sum of the EMF in a loop of the circuit has to be equal to the sum of the PD. Well, these are all going to be in the same loop. So effectively we could say that the voltage of cells in series is also something that just adds up, and therefore in this particular case we can state that the combined EMF, I'm going to call it the total EMF, is 3 lots of 1.5 volts, which is 4.5 volts, while the total internal resistance is just the sum of 3 resistances of 0.3 ohms. So let's write it out. 3 times 0.3, which is 0.9 ohms. 6 cells connected in parallel, so I'm not going to draw them all out. I'll draw a couple connected in parallel. And we can imagine they're connected to a circuit and it continues on underneath. So this time what we need to spot first of all is that we could draw an equivalent circuit to this because they are all identical, where the cells are connected in parallel and then the resistors are connected in parallel. So again, I'm not going to draw 6, but you can sort of imagine I ran out of space, so I've cut off the bottom half. We're going to have 6 parallel connected cells and then 6 parallel connected resistors. So the resistances in parallel we know about. It's 1 over R1 plus 1 over R2 plus 1 over R3, for however many we need, all to the power of -1. For the cells connected in parallel, again we need to fall back on Kirchhoff's laws, and what we'll spot is that the EMF across each of these loops has to be the same. In other words, that implies that the EMF difference between these 2 points in the circuit must just be the EMF of one of the cells. So multiple cells connected together in parallel don't give us a bigger EMF, but we have got this, which is going to help us. So this time the total EMF is just 1.5 volts, but the total resistance is 1 over 0.3 multiplied by 6, all to the power of -1. So 6 over 0.3 is 6 over 3 is 2, so 6 over 0.3 is 20. But this is to the power of -1, so this is 1 over 20, which is 0.05 ohms. So you can see the thing that it's not given us is a high voltage, but the thing it has given us is a much lower internal resistance. So we connect cells together in parallel to lower the internal resistance. Then the last part says 3 parallel branches, each containing 2 cells connected in series. So a setup like this would make more sense if the wires were here. So applying the principles that we've just said, we're first going to combine together the 2 in series. So for 2 in series, the EMF should be equal to 2 lots of 1.5, which is 3 volts, and the resistance should be equal to 2 lots of 0.3, which is 0.6 ohms. But then if I put 3 parallel branches of this, well, the EMF across each one is just the same, so the total EMF is still 3 volts. Having multiple branches doesn't affect that, but the thing that it does affect is the resistance. So I can imagine I'm now going to combine these two resistors I've put together already into a single 0.6, but now I've got 3 parallel branches of that. So the total resistance is 1 over 0.6 plus 1 over 0.6 plus 1 over 0.6, all to the power of minus 1. That's 3 over 0.6 to the power of minus 1. 3 over 6 would be a half. So this is 3 over 0.6 is 5, isn't it? So this is 3 over 6 is 5, so the reciprocal gives us 1 over 5th, so it has a combined resistance of 0.2 ohms. So our combined cell has an EMF of 3 volts and an internal resistance of 0.2 ohms.